Welcome everybody. I am Ariel, and today I will talk about my work within Smart in the last 4 years, talking about design and development of hybrid fuel cell / battery systems for underwater applications. So, to give a little bit of context, so the overall goal here is to increase the endurance and the performance of our AUVs, because as we've been talking before, we are having a lot of sensors, sonars, and communications in the water, and that has a cost in terms of endurance and energy. So the idea is to investigate the use of hybrid fuel cell and battery system to power the AUVs, and to investigate also different ways of storing hydrogen and oxygen. So I've been working on like 2 different levels, so to speak. So there's like a system design and modeling. So how do we find the best combination of fuel cells and battery in order to fulfill some missions? And also I've been working on like a lab scale in order to find the optimal conditions, working conditions for a fuel cell in a closed environment. So I'll talk about it later. But first things first, like why do we want to have fuel cell systems in an AUV? And why do we want to combine it with a battery pack? So here is the so-called Raguni plot, which is our favorite electrochemist plot. So here you can see the energy density, so the amount of energy per liter and of different electrochemical power sources. And here you can see the power density. And what we can see that fuel cells score quite high in terms of energy density, whereas batteries score quite high in terms of power density. Meaning that by combining fuel cells and batteries, we can actually achieve long-range missions, so high endurance, but we can also reach high power demand. So for example, when we have like a peak power demand, we need to speed, we need to dive, or we need to turn on some sensors. So there's an upcoming obstacle, for example. So the idea of hybridization is to combine the 2 advantages of those 2 electrochemical energy devices. So yeah, in the last 4 years, I've had a couple of milestones. So first was to find a methodology, like a strategy to optimize the design of hybrid systems. As I said before, also find the optimum operation points for a fuel cell in a closed environment, because in AUVs, you are working with in a closed environment. So you need to store both hydrogen and oxygen, and the conditions can be different compared to car applications, for example. We've been working on like creating strategies to share the power load between the fuel cell and the battery. And there are like some thermal considerations to consider as well when designing the entire system. So I'll go through like the different milestones and try to summarize everything here. But yeah, first things first. When I've started here, it was also like the first step was kind of to show that it was feasible to have fuel cells in AUVs, and to show why it was important and why it was useful, like kind of to convince. So the first step was actually to design a strategy, like to make out a strategy to optimize the system. So the idea is to find the best combination of fuel cell power and battery pack, so battery energy content, in order to fulfill the mission and to have the most compact system as possible. And by doing that, we compare several hydrogen and oxygen storage solutions. And we also compare with, so at the end, we compare the weight and volume with a full battery solution. So for the same energy content here, you can see the volume of different hybrid systems, depending on the way we store hydrogen. The volume of, the volume of a full battery pack. So for the same energy content, and the volume for a full primary battery pack. So those primary batteries are here like as a reference point, but they are not rechargeable. So it's nice for emergency missions, but on the long run, you don't want to have that. And in addition, we also consider like buoyancy, because we want the energy system to have a neutral volumetric mass. So we also consider different air or steel composition depending on the case. But I can explain to you how it works roughly. So within Smart, I was lucky to get some real power profiles, some real mission data. So from Hugin mostly. For example, this is like a 5-hour mission run by Hugin in Borno like 3 years ago. And what do we do here is the sizing tool that I've made uses those power profiles as an input, and then run an optimization process, and where we actually change the fuel cell power here. And we, in blue, you can see like the full weight, volume, sorry, of the hybrid system, depending on the fuel cell power. So the bigger the fuel cell power is, the bigger it will be. And you can see how the battery pack corresponding would vary as well. So you can find an optimum point here where actually you can fulfill the mission with the most compact system. And know that when you actually choose a proper fuel cell power, nominal power, you can compare different ways of storing hydrogen. So for this 5-hour missions, we can see that, well, all the hybrid system, they compete with the full battery system. But yeah, like the big picture for this study was actually this big graph. So what does it tell us here? Here we can see that in terms of energy density and specific energy, when we run short range mission, like 1 hour or a couple of hours, the hybrid systems, so fuel cell and battery, they score quite bad, meaning that it's quite complicated and it's not worth it compared to the energy density of batteries. But as soon as we increase the length of the mission, for example, 100 hours, 500, 1000, even more, we can see that in terms of energy density and specific energy, well, the hybrid system is always way better than the secondary battery system. Here, when we have like compressed hydrogen, for example, here where we have liquid hydrogen, you can see that we have a very high energy density and specific energy. And what we can also see here is that when you increase the length of the mission, at some point you reach an asymptote in terms of energy density and specific energy, meaning that at some point, the only thing that matters is actually the hydrogen tank and oxygen tank. And you can see that you're always higher in energy content than the secondary battery. So what do we learn from that first study? Like, well, this sizing strategy was developed and successfully developed. And the optimization guarantees that the system, that the selected system is the most compact, capable of fulfilling the mission. Yeah, the hybrid system becomes lighter and more compact than a full secondary battery system when the length of the mission increases. And yeah, that's kind of off topic, but we could implement that same strategy for another application, which was a rescue boat in a lake in Sweden. So we did exactly the same. We had some considerations and we had to create a power profile for it. But in that case, it was weight optimization and we didn't need to store oxygen, right? And we also didn't need to do like the buoyancy compensation. But we could see that we had quite similar results. So for like those boat applications, the hybrid system is always much lighter than the battery system. And when we have a very compact way of storing hydrogen, for example, liquid hydrogen, it almost competes with the ICE system, so diesel engine. That's kind of out of the topic, but it was a way to show that the developed methodology was kind of robust and could be implemented on other applications. But yeah, as I said, I've been working on this sizing and design of hybrid system, but I've also been working on lab scale. And yeah, hydrogen, like fuel cells they use hydrogen so that the fuel, and that's what we pay at the end of the day, right? And a good way to save as much hydrogen as possible is actually to close the outlet of the hydrogen channel to make sure that all the hydrogen reacts. So we have what we call like 100% of fuel utilization. But by doing that, you actually accumulate water and impurities within the fuel cell. So at some point, the performance of your fuel cell stack will decrease. So you need to open the hydrogen outlet every so and then to let the accumulated water leave and also the that can accumulate in the system. So we call it dead end mode, but we need to open the purge valve every so and then. And the game was kind of to find the optimal way of controlling a fuel cell working in dead end mode in a closed environment. So in order to do that, I built up a setup, which is a PEM fuel cell in a closed environment with hydrogen supply and oxygen supply. And we have a bunch of different sensors like pressure, relative humidity, temperature, hydrogen sensor in case of leak. And well, also hydrogen purge valve. And the idea was to perform a design of experiment on 6 different parameters and studying 2 responses. So the 2 studied responses were the time between 2 hydrogen purges needed, the time between 2 needed hydrogen purges, sorry, and the performance of the cell. So I can show you how it looked like. Ariel's box, don't touch the fume hood in my lab. So it's a bit messy, but basically you have all the electronics and the fuel cells in here. It's in the fume hood, and you have like the connections with the gas in here. But a better picture to show how it works, how it looks like. Those are PEM fuel cells from a Swedish company called MyFC, and they are composed of 6 cells in series. And the sensor cell here, you can see the fan, the oxygen valve, the hydrogen purge valve, microcontroller, some sensors here. And yeah, the major conclusions from that study were that, first of all, it was possible to find a prediction model to get the time between 2 hydrogen purges for PEM fuel cell working in a closed environment. And that's the most important part. So in such an environment, so in an AUV-like environment, the fuel cell should deliver a relatively low current density, so it produces less water. The forced convection should be limited in the system. And well, the closed environment should be maintained at a high relative humidity, so 95%, 100%. But yeah, to continue on this on this lab scale experiment, a new idea was to always the goal is always to improve the performance of the cell and to increase its stability over time. So we've tried a new approach, like we modified the setup. So we've added some valves, some free wire valves in the inlet and outlet. So it's a bit complicated here, but to summarize, after each purge of hydrogen here, we actually reverse the flow of hydrogen within the cell. So for example, first configuration, hydrogen goes from cell 1, 2, 3, 4, 5, 6, sub cell, then it's blocked. And then when we need to purge, we purge it. Then we close the voltage of the cell recovers, and then we close the purge valve, and the hydrogen goes this time from cell 6, 5, 4, 3, 2, 1, and it's blocked. So we call it symmetric purging strategy, or so we reverse the flow of hydrogen every time we need to purge. And the idea here is to have a more homogeneous water management within the stack when we run it. Because yeah, long story short, for fuel cells, stability is always connected with the water content within the stack. And the idea here is to compare the degradation of each individual cell. So we perform various electrochemical tests. So it's an ongoing study, but here are like some preliminary results. So here you can see the derivative of the voltage of the cells over time. And this is when we have the single purging strategy, so the first version. And this is when we have the symmetric purging strategy. So we can, right now it's a bit ambitious to draw big conclusions, but what we can see that we have way less variations with this symmetric purging strategy compared to the single purging strategy. So yeah, what we can say is that the symmetric purging strategy seems to maintain a stable overall performance of the stack and increases the stability of the stack as well. All right, so now let's jump to another milestone, which is actually a collaboration with Arsha and Clemens here. So we have two, in a hybrid system, we have 2 energy and power sources, aka the fuel cell and the battery pack. And the question is, how do we share the load between those two devices? And the answer is using energy management strategies. So as an EMS, it sets the behavior of a system based on its state and accordingly to a strategy. So basically, we have a bunch of inputs that we read on live, so fuel cell voltage, port demand, etc. It goes through an EMS, and then we set the fuel cell output power, the battery power, hydrogen consumption, and etc. And it has several objectives. So, well, the idea is to decrease the energy consumption, maintain a relatively high state of charge of the battery, and also use the battery and the fuel cell in a healthy way. I won't go too much into details because Clemens did most of it, but I can show how it looks like. It's a big simulator within Simulink, where we have all the different components of the fuel cell, the battery. We have the parasitic power here and different DC-DC converters. And the idea was to try some different energy management strategies and compare them. So we were quite lucky to have like some data from real missions. So we created 4 different EMS. So 2 were what we call rule-based strategies. So they are based on experts' knowledge. Basically, usually it looks like a lookup table. So it's based on what experts say, like, oh, in that situation, it's better to run the fuel cell in that way and the battery in that way. So we have 2 strategies like that. And we have 2 strategies which are optimized based strategies. So the idea here is to create a cost function and trying to minimize it over time. So here are like some basic results. So for a 7-hour mission, we can see here the 2 rule-based strategies, and here the 2 optimization-based strategies. And here you can see the state of charge of the battery during the mission. So we can see that here that for this mission, all the 4 EMSs can actually fulfill the mission. But we can see that, for example, the optimization-based strategy here in purple maintains a quite high state of charge of the battery and has more variations of the fuel cell power here as well in orange. Whereas, for example, this state machine EMS, it's a very stable fuel cell output power, but it depletes quite a lot of battery state of charge here. And when we look, for example, another mission, we can see that actually for some EMSs, the mission is not fulfilled because the battery state of charge reaches 0 or like 1 or 2%. Meaning that it basically explains why we are doing that. It's not just for fun or to show some Simulink skills, but it's to show that if we choose the wrong EMS for a mission, we are actually likely to lose the AUV or to fail the mission. But yeah, long story short, with those different EMSs, usually the optimization-based strategy tend to increase the state of charge to maintain a better state of charge of the AUV during the mission, but to deplete a bit more of fuel cell power. So it's always a trade-off. Like, what do we want to optimize, or what do we want to use more, the battery or the fuel cell? But it's not because it's a trade-off that we can't draw some conclusions or recommendations. So what we can see here is that like fuzzy logic EMS, like rule-based strategies, can be suitable for missions with low risk. For example, going around an algae farm, which is a mission that you will do every second day or every day or whatever, where there is few chances of losing the AUV, and where you want to decrease the hydrogen consumption because you will run it like quite often. But more complex optimization-based method can be recommended for missions with a high degree of uncertainties because, well, we want the mission to be fulfilled. So it's okay to consume quite more hydrogen. It's okay to pay more in terms of hydrogen if we make sure that the AUV comes down. All right, now the last milestone before I wrap up this presentation is the thermal management. So one question was raised that was, yeah, how do we include the total heat balance of a hybrid system on the design process? Because we have the fuel cell generating heat, the battery pack generating heat, and depending on the way we store hydrogen and oxygen, we might need heat or we might generate heat. So the idea here was to calculate the total weight, volume, and adjusted volume for each combination of energy storage, and to also calculate the total heat balance So here you see each Q is where there is like heat happening. So it can be heat produced or heat heated. And the idea, so we have different parameters that after we have the total heat balance, like in water, we have the weight, we have the volume, we have the volumetric mass for each combination of hydrogen and oxygen storage unit. And the idea after was to perform a multi-criteria decision-making analysis in order to rank those different combinations, because we needed an objective way to compare pears and apples. Like, how do we compare volume with energy in a decision process? So that's what we did. And we had 5 different criteria. So specific energy, energy density, volumetric mass, total heat, and the heat only for the storage. And we used 2 weighting methods. And we could see that the sum of the 2 heat criteria is kind of always the same for the both method. And when we rank all the different combinations, we can see that the ranking is also quite similar. And it showed that the combination of liquid hydrogen with liquid oxygen is actually the most promising one when we consider all the criteria. And the combination of liquid hydrogen with compressed oxygen or liquid oxygen with compressed hydrogen are also 2 very interesting combinations of reactant storage. Whereas, for example, the use of hydrogen peroxide as an oxygen storage unit is quite bad, or ranked quite bad. And we could also see that even when we increase the length of the mission, the ranking is always the same. So especially when we have mission above 100 hours. So it's that it's consistent over time. So yeah, some major conclusions for that study is that, well, chemical oxygen storage, so hydrogen peroxide, scores quite badly, so shouldn't be used in an AUV application. There is quite a big trend for like liquid hydrogen and liquid oxygen tanks. But what we could see is actually that the fuel cell is a major contributor to the total heat balance. So no matter which hydrogen or oxygen tanks we choose, we have to handle the heat from the fuel cell anyway. And we used an objective weighting criteria, and to further develop that strategy or that study, we should use also like subjective and practical considerations. All right, from a more academic point of view, to summarize what I've done here, so we could publish quite, not quite a lot, but a little bit on those different milestones. So we could publish the first experiment, like series of experiment, the design of experiment on the dead-end mode. We could, like, that is actually the most important one. We could publish the sizing strategy, which is kind of the base of all this PhD project. We could also publish the boat application, and we could publish the heat that I've study that I've just talked about. And we also contributed to different conferences. So some about AUVs and some about electrochemistry and fuel cells in general. And yeah, to like what's going next, like to finish this project, well, I will continue with the symmetric purging, try to improve the EMS, and I guess the end of the day, we want to scale up the experiments and have a fuel cell in an AUV. And that's all for me. Thank you.